Welcome to Chapter 3, Properties of Pure Substances. This chapter is the foundation of your understanding of thermodynamics. Every engine, refrigeration system, and power plant relies on the behavior of pure substances, like water, air, or refrigerants. Our goal is to decode how temperature, pressure, and specific volume interact, how to read property tables, and how to make sense of phase diagrams. These skills will help you answer questions like, at what temperature will this fluid boil under pressure? Or, how much energy is stored in this steam? Mastering these basics will make you faster and more confident when solving real-world engineering problems. Let's dive in and make thermodynamics practical and intuitive.
Let's start by understanding what a pure substance actually means. In thermodynamics, we're not just interested in what something is made of, but also how it behaves under different conditions. A pure substance has a consistent chemical composition. It doesn't change no matter how much you have or how you slice it. Water is a classic example. Whether it's ice, liquid, or vapor, it's always H2O. An important point is that a pure substance can exist in multiple phases, solid, liquid, or gas, but it must remain homogeneous. That means no visible separation or layering. Interestingly, even mixtures like air can be treated as a pure substance if it stays in a single phase and behaves uniformly. This simplifies our calculations in many engineering problems. The key takeaway? Pure substances give us a stable, predictable foundation to apply thermodynamics effectively.
2. Phases of a pure substance. Let's break down the 3 basic phases of a pure substance. This is the foundation of understanding how matter behaves in thermodynamics. First, the solid phase. Molecules are tightly packed with strong bonds. They don't roam around, but vibrate in fixed positions, which is why solids hold their shape. Next, the liquid phase. Here, the bonds weaken. Molecules move more freely while still staying close. This gives liquids a definite volume, but no fixed shape. They flow. Finally, the gas phase. Molecules are far apart with very little attraction between them. They move rapidly in all directions, filling up any container. Understanding these phases helps you predict how a substance will respond when you change temperature or pressure, something every engineer needs to master.
3. Phase change processes of pure substances. Let's make sense of how pure substances change phase. This is where thermodynamics gets really practical. First, a compressed liquid, also called subcooled liquid, is nowhere near vaporizing. Think of cold water from a tap. It's liquid and stays liquid. Next is the saturated liquid. This is liquid right at the boiling point, just ready to vaporize, like water at 100 degrees Celsius under atmospheric pressure. Then we have saturated vapor. Vapor that's about to condense back into liquid. It's like steam hovering right at its condensation point. When you heat beyond that, you get superheated vapor, steam at a higher temperature than its boiling point at a given pressure. And finally, latent heat, the hidden energy that causes phase change without temperature change. There are 2 types: latent heat of fusion, energy to melt a solid into liquid; latent heat of vaporization, energy to vaporize liquid into gas. Understanding these terms helps you solve real engineering problems, like designing boilers, condensers, and refrigeration cycles.
4. Property diagrams for phase change processes. Let's simplify property diagrams. These diagrams are the maps that show how pure substances behave during phase changes, like a GPS for thermodynamics. The TV diagram plots temperature against specific volume. It's great for visualizing how heating or cooling affects volume during phase changes. The PV diagram shows pressure versus specific volume. This is crucial when analyzing compression and expansion processes like in engines. The PT diagram is pressure versus temperature. This is your go-to diagram to understand boiling and condensation at different pressures. Now, 2 special points. The critical point is where liquid and vapor phases merge into one. Beyond this point, there's no clear phase change, it's just fluid. The triple point is where all three phases, solid, liquid, and vapor, coexist in perfect balance. These diagrams help engineers predict and control phase changes in real systems, from power plants to refrigerators.
5. Property tables. Let's talk about property tables, your go-to tool for solving thermodynamic problems quickly and accurately. Start with the saturated liquid and saturated vapor tables. These tables give you the properties of liquid and vapor at boiling or condensation points, making phase change calculations easy. Then comes the saturated liquid-vapor mixture. Here, we use quality, or X, to measure how much vapor is in the mixture. It's a simple ratio, vapor mass divided by total mass, giving you a quick way to estimate properties in mixed states. Next is the superheated vapor table. This is for when vapor is heated beyond its boiling point. Temperature and pressure are now independent, and you need these tables to know enthalpy, internal energy, or volume. Finally, the compressed liquid table. Since data is limited, we often approximate compressed liquid properties by using saturated liquid data at the same temperature. It's a useful shortcut when pressure isn't too extreme. Mastering these tables saves time and boosts your accuracy. Key skills for any engineering exam or real-world system analysis.
6. The ideal gas equation of state. Let's discuss the simplest but most widely used equation in thermodynamics, the ideal gas equation. The core equation is PV equals RT. Simple, but powerful. Here, P is pressure, V is specific volume, R is the gas constant, and T is temperature. The gas constant R is unique for each gas. For example, air and steam have different R values, and you'll always need to use the correct one for accurate results. Now, the ideal gas assumption simplifies life. It works well when the gas is at low pressure and high temperature. Think of air in normal conditions. But it breaks down for high-density gases like steam near saturation, where intermolecular forces become significant. The takeaway? Use ideal gas equations when applicable, but always check the validity of the assumption, especially when working with steam cycles or refrigeration systems.
7. Compressibility factor, Z. Let's look at how to correct the ideal gas equation for real gas behavior using the compressibility factor, Z. Z shows how much a real gas deviates from ideal behavior. When Z equals 1, the gas follows the ideal gas law perfectly. When Z does not equal 1, it means there is a deviation, often due to molecular forces or high density. Z can be calculated in two ways. Z equals PV over RT, which compares actual pressure, volume, and temperature to the ideal gas equation. Z equals V actual over V ideal, which compares the actual specific volume to the ideal specific volume. To simplify calculations, we use the principle of corresponding states, which says all gases behave similarly at reduced pressure, PR, equals P divided by P critical, and reduced temperature, TR, equals T divided by T critical. With PR and TR, we can use standard compressibility charts to estimate Z for any gas. This avoids complicated calculations and improves accuracy for real gases.
8. Other equations of state. Let's discuss more advanced equations of state useful when ideal gas assumptions just don't cut it. First, the van der Waals equation. This adjusts for two real-world effects, molecular attraction and the finite volume of molecules. It's simple, but a big step up from ideal gas. Next, the Beatty-Bridgman equation. It uses 5 constants and improves accuracy, especially for moderate pressures and temperatures. Better than van der Waals, but still manageable.
Finally, the Benedict-Webb-Rubin equation. This is a high-accuracy model with 8 constants, used for precise calculations, especially in high-pressure applications like chemical plants. Each of these equations adds more complexity, but also more precision. The key is knowing when higher accuracy matters and when simpler models are good enough.
9. Vapor pressure and phase equilibrium. Let's wrap up by discussing vapor pressure and phase equilibrium, two key ideas for understanding evaporation, condensation, and humidity. Vapor pressure, PV, is the pressure created by vapor when it is in balance with its liquid. For example, if you leave water in a closed container, some of it evaporates, and the vapor pushes back on the liquid with a certain pressure. This is the vapor pressure. Relative humidity, phi, explains how much vapor is in the air compared to how much it can hold at a certain temperature. The formula is PV equals phi times PS at T, where PS at T is the saturation pressure at temperature T. When phi equals 1, the air is fully saturated. No more water can evaporate. When phi is equal to 0.5, the air holds half the maximum moisture. These concepts help you understand practical systems like air conditioning, cooling towers, and weather patterns.